Good morning, everyone. It's nice to be back again in our colloquium presentation series. So we are fortunate enough to have Mr. Paul for today's presentation. Paul Preney he has an MSc, a BSc, and BEd. He is also an Ontario certified teacher. He is a subject matter expert of various standard district committee, including IPC Club one that we discussed. He taught social in our university, and also he is a on-campus SHARCNET staff person. So if you have any difficulties or if you have any questions regarding the Compute Canada, Paul is the person to go. So thank you, Paul, for joining us today. If you are ready, we'll be.
Thank you. I don't know which mic is doing the transcribing in that. Is this one probably, yeah, right? So I'll tend to stay here, although I like to walk around in this room, but I'll stay here more. My name is Paul Preney. I should mention my undergrad, the Bachelor of Science, is in both biology and computer science. My master's is in computer science. So I am on the ISO C++ committee. This talk, I'm going to first talk about SHARCNET. We're currently upgrading nearly all of our hardware, and it's in various stages of upgrade. So I will give you an update of what to expect. Given that this room is filled with basically one way or another computer people, you're going to like the hardware. It's cool stuff. And then after that, I'm going to, so I'll just give you an overview, but there's nothing you can log into that's new yet. So we can hold off on that presentation for later. Not long from now, actually, later in the year. But I wanted to talk about what's coming. Very, 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 very likely. Sorry, I got to say it that way. These things are already voted into the next C++ standard. So if they don't come, that means I and the others on the committee voted them out of the standard. And that has happened before. Things that everyone wanted in but weren't ready and unanimously were voted out. Okay, that happened with C++, the 2011 standards, C++ 11, and with concepts, and it took all the way until 2020 to get concepts into the standard. There's a bunch of things that are being worked on that they're all good stuff. And if you are into at all anything, well, we typically would say high performance computing, but if you're in AI or anything like that, linear algebra is good stuff. Linear algebra is coming in, and it is based on BLAS 1, 2, 3 stuff. Okay. Hazard pointers and RCU for parallel programming. Those of you who know anything like that or want to do that, that's good stuff. SIMD is also for parallel programming. It's a little bit different. I'll talk less about it, but these things are useful to know. Okay, which keyboard? This one right here. Okay, so just mention University of Windsor. We're on the Three Fires Confederacy. It's a Ojibwa, a Dawa, and a Potawatomi in tribes, and this area is famous for it. So if you've not checked any of those things out, there's plenty of locations here on campus in this region, and the history. We go back to the first settlers and all that. And I'll just put it this way, the way my dad's side of the family, which they've been here for a very long time. They said, basically, think of it this way. Highway 3 that runs through Essex County, the original Highway 3, old Highway 3, is the highest point in the county. Any other hills, man-made. Okay, Micmac Park and all that, that's all man-made stuff. So landfill hills and that, those are all man-made. The highest point really is Highway 3, and outside of that, the natural stuff, maybe a little bit of the hills you get in Amherstburg out towards Seacliff as you go towards Leamington in the southern part of the county, but the rest of the county is pretty flat. It's so flat. I'm a longtime member of the Windsor Center of the Royal Astronomical Society of Canada. There's a certain number of die-hard amateur astronomers that every year in March, there's this galaxy 5128, NGC 5128, that due to the index of refraction, appears above our horizon where we are. So they head out to Point Pelee early in the morning, very early. There's certain things you got to make arrangement. You just can't show up there. The ranger won't let you in. Okay. They show up there and they try to see in the index of refraction this galaxy. And over now, I guess decades, a couple of people have successfully done that. That's how flat Essex County is. And Point Pelee, though, if you think about it, you have a nice flat lake there, right? As long as you don't have any nasty winds or storms going on, you're okay. Sounds silly, but it is fun. And if you are into astronomy, challenge object. SHARCNET stands for Shared Hierarchical Academic Research Computing Network. Most people don't know that, but now you know. Okay. We provide access to high computing resources, cloud, and lots of storage. Okay. And we do a whole bunch of training. So we get provincial and federal funding for this. Okay, it started in 2001, and it's something like 19 Ontario universities and colleges. The ones that aren't in the list are fairly easy. SciNet, okay, that's University of Toronto, and the Center for Applied Computing, they usually just say PAC, those are the rest, a handful of universities not in SHARCNET. Okay. Compute Ontario, so in terms of funding, now most in this room don't have to worry about that, but those who worry about grants and all that, provincial funding needs to go to provincial entities and federal funding needs to go to federal entities. So Compute Ontario is the provincial entity that gets funding and we're under it. And also under it, besides SHARCNET, SciNet, and the Center for Advanced Computing, is HPC for Health, and that's the hospitals like Toronto Sick Kids. HPC for Health is on its own. For those of you, some of you already know, but maybe you don't, healthcare, there's a lot of legal, ethical, and other considerations for every project that you have to go through. Ethics, all this stuff, clearances and that. So they're under their own umbrella. So if they interact with us, it's special case, quiet behind the scenes. But they have their own stuff. Now, across Canada, originally it was called Compute Canada, and I preferred that name. Quick aside, in the US, they used to be called Exceed. Okay, you can Google for those names and get somewhere. Exceed is not spelled the English word; it's spelled with X and SED. But those are the old names. So Compute Canada, I won't go into details, but they renamed themselves to the Digital Research Alliance of Canada. That's way too long. So they like to say the Alliance. Good luck Googling on that. You can Google on the whole thing, but if you just Google on Alliance, you're going to get everything. And it's just like in the US, they renamed themselves to a longer thing, but Access is the main thing. Good luck Googling for that. I don't get it. But the technical people aren't choosing the name, so it is what it is. Across the country, we have AceNet, that's the Atlantic provinces. We have Quebec, Compute Ontario, and then it's still up in the air. I don't know exactly what they're doing because they don't really have a website or name, but Manitoba West, you can think of them as roughly all one big region. Okay, split in the prairies in BC, but these entities are there for the funding and all that stuff. And so if you're a faculty member, then maybe more relevant, but if you're just using our systems, not very relevant. So research, we support research. Okay, this is not for profit stuff or mining Bitcoin or anything like that. This is for the support of doing research. So the research projects you're doing under your supervisors and things like this are the kinds of things done on it. Okay. Supercomputers. Well, these days, I think it's easier to say, you know, you got your laptops, all that stuff. Well, think of your laptops in well, it's not one core, but you know, you got one CPU and a few cores on it. If you just think of that as like one little piece, Okay, and when you run something on it, fine, but if you need 1,000 little pieces, you got a problem. Where do you go? Okay, so our systems are a network of thousands of computers or nodes. And each computer will have some number of cores and a large amount of RAM and all this. And it's all set up for compute staying on and running 24 hours a day, 7 days a week, 365 days a year, nonstop. The equipment that you need to do that is more expensive. If you did that with your laptop, you would burn it out in about 4 months, running it at max. These systems are typically running max, solid, all the time. There's various kinds of interconnects and all this stuff. It's the enterprise stuff. Your laptop is a consumer thing. Enterprise stuff is more expensive. Yes?
Was it like how one of the hospitals made a supercomputer out of PS3s? Kind of something like that?
Sorry, hospitals?
Well, a hospital used a bunch of PS3s at the time since they were cheaper than supercomputers.
Yeah.
And they all banded them together to do research.
Yeah, and that's basically what happens for your clusters. You take a bunch of computers, you connect them all together. If you're thinking low tech, you could connect them with like Ethernet. But the interconnects are way more expensive than that. Or if we do use Ethernet, like the new system SHARCNET will be running and will come online in the next few months, that is Ethernet, but it's all very high speed, low latency Ethernet. And the switches are expensive.
What's the highest cat?
Right.
What's the highest cat right now? Like Cat 6, Cat 7 for Ethernet?
I think the highest cat is 7, but I don't normally worry about it. Server room at Graham used to look like that. The new cluster coming in is in tanks. The computers are actually in a type of mineral oil. There's even a crane to lift them in and out and all that stuff. Had some fun talking the other day with one of the sysadmins saying, this is a fun experience. And I said, so how is this? You have to get like special gear on and stuff. And he said, well, if you have to reach in and grab something ever, he says, understand these big tanks are like those racks. Turn them on their side, and he said they're easily 4 feet deep. Now, the temperature of the oil is a little bit more than room temperature. I don't remember what it is, so technically human arms could go in there, but they're going to use the crane and all that stuff. And whether you realize it or not, unless you're into the hardware or sysadmin kind of thing, things go down all the time. Obviously, brand new stuff, it's mostly money, but over time, things go down. And even though the cluster has thousands of whatever, sysadmins will say, oh, we got to shut down node whatever, drain the jobs from it, get them going somewhere else. And then they got to take it out, replace something and put it back in and all that. That happens frequently. Okay, so right now, there's Beluga, Cedar, Graham, Narval, and Niagara clusters. The Niagara cluster is special purpose for large jobs. The rest are general purpose clusters. And this is what's in them right now. Now, the only cluster that will remain past, well, I'll say for sure past July, Narval. All of the other ones will go bye-bye. But they've been running for over 5 years now. They're going bye-bye. Okay, what will be up is Narval, in the previous slide, and these. So the new one, the Cedar out in British Columbia, is the Cedar one. That the new cluster will be called Fur. The new cluster for Graham that SHARCNET runs will be called Nibby. It's an indigenous word for water. The Telco Quebec will be running Rorqual and Narval, and SciNet will be running Trillium. Now, the thing to note between this slide and the previous slide is if we just take, for example, Graham, we are at 1,300 nodes. So that means there's 1,300 computers in there. If you're thinking that's a lot of power, it is. If you're sitting with some of the sysadmins and all that stuff, they would be talking about megawatts of power. The people worry about money with the province and other things and grants. They budget for megawatts of power use per annum. Okay, it's not a small amount. So with NIVI, we're going to have 752 nodes. Now, just to give you an idea here, if you're used to running a job and you say, oh, I want the whole node to use for my job. Well, on Graham, that node probably has 32 CPU cores. Okay. And approximately 4 gigabytes per CPU core of memory. Okay. On NIVI, that node will have 192 cores, and the amount of RAM will at least be 4 gigabytes. It might be more. Okay. So the numbers go down in terms of number of computers, the nodes. Okay. But the number of cores is going up. And if you're astute, because I flipped fairly quickly there, if you're astute on it and you notice the GPU count also drops. Okay, but the power of the GPU, what they can do, is much higher. Now, the reason I'm mentioning this is the number one problem that we're sort of anticipating, especially with GPUs, but I think it's going to happen with CPUs as well, is people's jobs which formerly utilized well the cluster. If you run them under the same set of commands and stuff that you did, they're not going to have good utilization. We're feeling GPU utilization might drop really small numbers. It's already small, it might drop even more. The way around this, there are some ways around this that we're going to deal with the GPU, but for CPU, everyone will have to shift their jobs. And if you were doing a whole node thing, expecting 32 cores, well, that whole node job, if you didn't change anything, the system would just assign you 192 cores. And of course, that would lower your priority relative to others because say, hey, I just gave you 192 cores and how many gigabytes, not gigabytes, some machines, terabytes of memory. And you're going to say, I got to do something here. You got a question?
Well, yeah, since they're using new GPUs, would it be like if they're running the same code, would it be optimized for the older GPUs and they're not using the whole, like everything that they've been giving like resources?
I'll simplify the things for GPUs, except on Narval, which is the older cluster. All of the new clusters, all the new hardware will have NVIDIA H100s, okay, with NVLink interconnects, okay. NIVI, the one SHARCNET's running, that all of the GPUs, okay, almost all, literally, will be 8 times with interconnects, okay? All of the other clusters will be 4-time interconnect. But we are thinking of not permitting people to run and exploit that until they do certain things because we want to know their usage can be high enough and not 0 or effectively 0. These GPUs, unlike your graphics card in your computer, these GPUs can run full tilt 24/7 for years on end without fail. If you did that with the GPU, you bought a high-end NVIDIA GPU, put it in your computer, great for burst things, gaming and all that, but I guarantee you, if you ran it like people do on the cluster doing compute, 6 months, it would be dead. It wouldn't work anymore. Right? You'd be buying yourself a new card. So the video outs on the compute GPUs don't exist. So they're just like the graphics GPUs used for gaming in terms of programming and all that, but there's no video out and they're just meant for pure linear algebra, which if you look at a GPU and the low-level commands you can use on a GPU, you will say, hey, this is all linear algebra. All the bitmap transforms, they're all just linear algebra. And that's how it's used on the cluster. Now, the one unusual thing on NIVI will be, we will have some nodes with AMD APUs, they're MI300A chipset. That's the chip and the GPU are sort of on one motherboard. Okay, so that's pretty cool. And I suspect maybe the AI machine learning people will be most interested in that, but there are a number of applications where that could be. The issue with GPUs, of course, all the GPUs are discrete except for the APUs. And the issue is the number of lanes of bandwidth on the motherboard to transfer the data back and forth between the GPU and the CPU. And if you don't have enough data, that means it can take too long to do that and make it not worthwhile computing on the GPU. What most people do that use GPUs, put stuff on the GPU and you try to run things as long as possible and do the most things on the GPU before transferring data back. Okay. All of our systems by design per CPU core, there's 4 gigs of RAM. I just put raw totals here. I totaled them up, but it's each CPU core, we design it so it's about 4 gigs of RAM or higher. And all of our systems are Linux systems. So if you know how to use Linux, great. Because you log in and hey, it's Linux and you're familiar with it. There's a bunch of things, there's certain things set up. And if you think they're a little bit strange, fine, but if you log into other clusters, you'll see they do the same thing. Okay. Yeah. C++. So, C++, those of you follow ISO stuff at all, there's numbers for everything. 14882 is the number for C++. But the current standard is C++ 23, the 2023 standard. It took over a year for the ISO to approve the document. So people like myself, the subject matter experts, we vote on the document. And then the ISO people in Geneva, Switzerland, do their editing and stuff. And they can't change the content, but because we approved it, right? But they do fuss about the editing. And they took a really long time for the C standard, which is C23. They took a really long time and got released in late 2024. I know the C++ one, I voted in the beginning of 2023, in February or something, if I recall. And then shortly thereafter was the C++ one. So the next standard, we're on a 3-year release cycle. So if any of you notice, C++ 11, C++ 14, C++ 17, C++ 20, C++ 23, C++ 26. You say, is there C++ 29? Yes, that's exactly the pattern. Every 3 years, we're releasing new standards. So the next one will be 2026. That will be voted on very likely in February or March of 2026. And hopefully it only takes 6 months for the thing to come out of the ISO, but we have little control over that. But we move on. We keep standardizing, moving forward. Okay. My advice to people, prefer using the latest C++ standard. Okay. If you are doing anything, and I mean anything with concurrency, use C++ 11 or newer. If you're using C, use C 11 or newer. C++ 11 and C 11 were released at the same time, so the definitions for concurrency would match in both languages. And prior to those standards, things, yeah, worked for parallel stuff and all this, multi-threading and everything else. They worked because compiler vendors and everyone made things work, but it's not guaranteed to work. There's nothing in the standards for C and C++ prior to the 2011 standards for them that ensured concurrent stuff works properly. Okay. If you're using older standards, then I recommend you use the newest, oldest standard you can use. Put it that way. My personal preference is C++ 14 is like a bug fix on C++ 11. It's not really a great description, but good enough. So I tend to use, if I'm forced to C++ 11, great standard, big deal. After that, originally I would have said C++ 17, but I'm now leaning towards C++ 20 is a better choice because of concepts and some other features in it. So what's in these standards? So C++, the first standard in 1998, not fine, that's the first one. A lot of people, when they take C++ courses or do whatever, pet peeve of mine, pet peeve of people who work at Bloomberg, Forbes, Meta, all this stuff, people on the committee talk to. And this includes Ivy League universities all the way across. A lot of people teach C++ or cover C++ the way they were taught, which was decades ago, because it was how that person was taught and how that person would keep going back. And then we're talking what, before the first standard even, okay? Totally different world. C++ 11, totally different world, okay? When C++ 11 was approved and came out, people said, wow, C++ is like a new language. It's still the old language. You can do everything you used to do, but there's a whole bunch of new features. So this is just a list of some of the things. One of the things that C++, but I'll just talk about C++, has been focused on is putting a bunch of things in the language that really should be there. A mix of low level and higher level and in between. Now, a really big deal of C++ 11, a really, 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 really big deal is move semantics. So when I taught the C++ course, I would emphasize move semantics a lot. You can gain a lot of efficiency there. There's a whole bunch of things. Now, when you did, if you're in computer science, you did the compiler course, the honors program at least, did the compilers course, you learned there was L values and R values. That's naive. It's been naive. C++ has shown it's naive. There is a larger taxonomy than L values and R values, and us exploits them. Okay, so move semantics is a very big deal. An L value is something that can be on the left-hand side of an assignment. An R value is something that cannot be. Okay? That's the naive view of it. And the taxonomy was realized back in the 2011 standard when they're dealing with it, that things need to be more detailed. I'm not going to go into that here. Concurrency semantics were added. Now, if you need to do concurrent programming, multi-threading stuff, whatever, the languages in the world that have well-defined semantics, at least in some de facto standard or standard documents, are C++, C, OpenCL. Okay, from the kernel group, OpenCL stuff. This definition go between them. If you look at release dates and you keep going, you can see, hey, these definitions look like they're all connected, and they are. Okay. Java, another one. Microsoft has heavily made C# obey the definitions for concurrency and all that. And memory ordering is huge. If you think, oh, memory ordering, what's that? It's all about it. The only way to grab a lock on something or to do things is you have to have a memory cell involved somewhere. And the ordering of operations on that memory cell is absolutely critical. And the low level side of things, you have stuff called atomics and things like that. So the standard brought in thread local storage, a whole bunch of low level primitives, although some of those you might say are high level. In the scheme of things, they're low level. The C++ standard the committee realized we can no longer play games with null for the 2011 standard. So there's a special type, null PTR underscore T, and there's a special one value, null PTR. It's a keyword in the language, okay? And that type gets converted to whatever the null pointer type is of whatever pointer thing you're using. It is so important and thorough, the C standard and the latest C standard just added null pointer to the standard. And if you're wondering why it's not null, NULL, because the C++ committee had all of the people involved with the committee and people they knew search all their code, of decades of code, for hits and misses. And the word null, capital or nil, this, that, ding, 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 you go through them all. They were all used, but no PTR wasn't used, right? Or I think it was used somewhere, but they said, oh, we can search and replace them. So that's what we went with. So it doesn't conflict with anything. That's why it's no PTR. Okay, auto and decal type in object-oriented programming, final and override. A line of and a line as. Many of you might not have thought of it when you write code. The alignment, where things are put in memory matters. Now, if you're used to good old Intel CPUs, it doesn't matter because you can put everything pretty much anywhere and it still runs. But most hardware, if you have an integer at the wrong address, there are incorrect addresses, okay? If you have the integer at the wrong address or a float or whatever, that computer is going down. It's halting, it traps. Multitasking operating systems, it will kill the program, but you need to worry about alignment. And if you want to worry about efficiency, you definitely, even if the computer allows you to do it, you definitely need to worry about alignment. If you're going between hardware like GPU to CPU, alignment matters. Most GPUs make the alignment the same as the CPU hardware they are mostly run on. But quick aside, you can put an NVIDIA GPU, as long as you have the drivers for it, into non-Intel hardware system. That works. As long as you have the right hardware interface and drivers, you can do it. Static assert was added to the language. That's like assert, except it's at compile time. And unlike other things, static assert, immediate compiler error. So it has to be true. Has to be true when it's there, or it's compiler error right on that spot. Const expr and no accept are both very big deal. So many of you here have programmed in Java or seen it. Java has throws clauses that you can say this method throws an exception, and you say which ones. Okay, Java has that. C++ had that. And it was deprecated and removed. It was discovered that that creates a lot of problems for a lot of systems, let alone real-time systems and safety critical systems that need to be up and can't be shutting down because you violated an exception. Okay, so what you can say now, and it's actually part of the type of a function as of C++ 14, you can say something is no except or not, and you can test whether or not it throws exceptions or not. So it's an all or nothing. So most functions can throw exceptions, and you just don't say anything. And on the ones that are guaranteed to never throw, and I mean guaranteed, because if they do throw an exception, everything shuts down. That's no except. Range for is the for loop that you all saw in Java for some value colon some container. Okay, that's in C++ now. That will work with anything that is a range container if you're used to that, but the term range is a better one to use in C++. In other words, it's a begin and begin and end both, begin returns an iterator, end returns something that is an iterator or a sentinel. Okay, lambda expressions are functions without a name. So that's what that is. C++ 14, minor evolution. A bunch of things were added. Classes, functions can be templated. Variables can be templated in C++ 14. Okay. Const expr. Why did I say to use the newest standard possible? With each standard, const expr has been relaxed and relaxed and relaxed. Const expr functions in C++ 11 had to be exactly one line of code. C++ 14, they can be many lines of code. Way easier to write. If you're in C++ 11 and you want to write a const expr function in one line, you will need to resort to metaprogramming to do it in some cases. In C++ 14, you can just write it. In C++ 14, you can have an auto return type. In C++ 11, an auto return type still needs the proper return type specified at the end of the function. Okay. There's digit separators, things like this. C++17 brought in a whole bunch of things. One of the things I think is unsung, more people should realize it's there, is file system. So suppose you want to process things on the disk. You want to recursively search all directories through all files, following all symlinks or whatever. That's what file system lets you do. But because C++ is on all platforms, and this went through 3 rewrites before getting into the standard, this will work on Mac, PC, Linux, you name it. You can just search the whole file system. So you can write code now that searches the whole file system, opens files, looks for stuff, whatever, and that code will run the same in 10 years. It is in the standard. That's another reason for standards. Okay, some people say, oh, I put this in a scripting language. Yeah, but try writing that script in 10 years. Okay, or Python, when it evolves to do whatever, it's going to break. A big reality of ISO standards is, in the IT world, is backwards compatibility. Talk about it all the time. So if we break something, there's something that replaces it. Okay? And we try hard not to break things. More const expert. I won't even go there. Fold expressions. Those of you who like to think recursively and do things like this and say, hey, can we just take all these template parameters and do the logical and on them and get the result and go like ... That's what fold expressions are. They're beautiful. Okay. And then something really cool was previously done with functions, but now in 17, class template argument deduction. So these are classes you write. There's template parameters and everything. And within certain limits, the compiler is able to determine what the template parameters are to the class based on the constructor types, the arguments of the constructor types. And you can help the compiler too. You can write little things in the code to tell it. And this allows people to not have to write all the template parameters for their types. And if you've done any C++ programming, say, hey, this is pretty cool. I can do this with functions and I don't have to list what all my template parameters are. Well, you can do that with classes now. C++ 20, by far, the biggest thing, in my personal opinion, in C++ 20 is concepts. And as I said, C++ 11, concepts was thought of, and then it went through a few more reworks, became tractable. See, the version of concepts in C++ 11 was not running in polynomial time, big time, whereas concepts in C++ 20 runs in polynomial time. Those of you who aren't thinking of complexity so much, let me just say this. Concepts are Boolean values. And whether or not something satisfies a concept is equivalent to satisfiability problems. Okay, so think of all your 3-sat, this and that, satisfiability problems, and it's so easy to get into a situation where you leave the world of polynomial complexity class and you're in NP and worse. Okay, so concepts are applied to templates, and the way I'd like to describe them in a quick way without touching upon them and showing examples is originally in C, functions didn't have prototypes. Originally, go way back, way before the first standard. Okay, so function prototypes are to functions as a comparison, as concepts are to when you're using templates, concepts or generic programming, concepts are to not using concepts. Concepts can be used with anything that's templated. So I don't want to say classes or functions or whatever, but concepts allow you to check if things conform, and they are interface checks. They're not semantic checks, although some of them could be semantic. They're actually the interface of your objects. Okay, I won't be surprised. I've said this and when I've taught classes and other presentations, I won't be surprised if in some years' time, I don't know, 10 years or so from now, we are more likely talking about concept-oriented programming than object-oriented programming. But we'll have to see how this evolves. One of the things everyone thought concepts would help with are the error messages. Because when you use templates, heavy template use, generic use, you get weird, crazy error messages. And you kind of need to be an expert to figure it out. Concepts do improve that, but not in the way everyone quite anticipated. Modules, I'm happy to say, finally, C++ 26, I think. There is a STD and an std.compat module in the standard coming to be. So maybe all the compiler vendors, by the time C++ 26 gets implemented, they'll be happy, and then you'll be able to just, like in Python, you load your module, you'll be able to load the std namespace in C++ and just write your code. You won't have to put 29,000 includes. Yes.
The STD module, do you mean 23 because it's in 23?
Yeah.
So isn't it in 23?
STD
Module
might be in
module.
23. Yeah, there might be something in 23 and 26, but no compiler vendor has fully implemented it yet. So, you know, we're waiting a little longer, but it's coming. Ranges. Okay. The ability to start at the beginning of a container, going to the end of a container. You want to think of it that way. Think of an array or a list or whatever. Okay, if you want to think of that, going from the beginning to the end, that's a range. Okay, and in C++, containers you want to think of in terms of ranges. Now there's a whole ranges set of thing in C++ and all that stuff that are quite aside from your containers. And it is more based on functional programming things, but that's in C++. Very big deal, three-way comparison operator. So how many of you, when you do less than, greater than, is equal to, all this stuff, they return Booleans, right? And you might say, wouldn't it be nice to have one operator and you can say less than, greater than, whatever, just tell me what it is. That's what the nickname is spaceship operator, because it looks ASCII art for, you know, like Star Wars, you know, stuff. If that means anything to you, fine. I date myself, I guess, a little bit on that, but unofficially, everyone calls it the spaceship operator. But what is cool about it is the semantics were brought into the language to have that operator automatically do the right thing. In just about all the cases, in even so much so that if you do things properly with your types, you can go equals default and the compiler will automatically write the efficient code for you. And yes, the committee did think about how to define everything for efficiency. Okay, so concurrency stuff, C++ 20 is big. Coroutines, you don't know what a coroutine is? A coroutine is it's an old idea. It's a function that can be suspended and resumed. Yes, there is an end of that function if it ever ends, but it can be suspended and resumed. Very importantly, C++'s coroutines are stackless. The only stack in a coroutine is that function. When the function actually runs, it uses the call stack on the thread it is run on. When it's suspended, it gets taken off the thread. I say that because other languages that have coroutines are stack full. And the entire stack that the coroutine has is part of their thing. This makes them inefficient. In C++, a lot of work was done to make them extremely to the lowest level efficient. Most of that work was done at Microsoft, but they're in the standard. Coroutines in C++ are also unique compared to other languages because you can suspend a coroutine. It's cooperative multitasking if you're thinking here. You can't force suspend it. It has to go itself. But you can suspend it on one thread and resume it on another. The coroutine, if it doesn't check, would be completely unaware of this. Okay. Then there's latches and barriers and semaphores and all that stuff. C++ 23 has a bunch of things, yes, standard and standard compat in it. So maybe the next, I don't know, 5 years, compiler vendors will finish experimenting with modules, which has been in C++ since 20. There's a lot of issues being dealt with. That's why it's still experimental for most compilers, all of them actually. But C++ 23 has the multi-dimensional subscript operator, okay, MD span. Those of you who've been wanting to do multi-dimensional array bracket things, say in C++, you'll be happy. Maybe not super, super happy. You'll say, oh, my favorite programming language lets me do it with everything. Sure, okay, but it's there now. And there's a little piece in C++ 26, but if you can use it now with the reference implementations, and the little piece in C++ 26 has been backported for it. I'll just word it this way. This has been wanted for a very long time. Expected, those of you like Rust and all that, some languages that let you return an error or an exception. Expected is a type that does that. It holds an expected value, expected type, or some error value or exception. There's a bunch of things that people have been wanting. Suppose you have high performance computing is a lot of arrays, vectors and stuff. Suppose you want to treat that array like a set or a map. Well, there's been types added to do exactly that. But C++ is nearly completely generic, so any conforming container type can be used, not just array. And generator is the only useful coroutine in the C++ standard. Okay, it's very cool. The reason there's not other ones, it's not so easy to write coroutines that are absolutely robust. But generator is very good. What it does is, the idea is you have a function and every time you suspend, you return a value. So you're for loop and you return a value, you return a value, you return a value, you return a value, you return a value. And each time you call it, it resumes where it's left off. So it's called generator because it looks like it's a big container, but it's like lazy evaluation for the next value. C++ 26. Reason for today's talk, so I'll just quickly go over this. Give you a sub-MD span is taking slices of your multi-dimensional arrays. Those of you who already do linear algebra and have done it in other languages, I don't know, Fortran, MATLAB, whatever, you can do slices. All of that. Okay. The libraries that have been backported support sub-MD span. Sub-MD span is a function that returns an MD span. MD meaning multi-dimensional. Linalg header will be linear algebra. Okay. Hazard pointers, RCU and SIMD have headers and their types on it. So, subscripting. If you need subscripting, I put in slides here. There's the Cocos reference implementation, and some people ask me, they say, well, does it bring the whole Cocos project in? No. If you're using Cocos already, you don't have to do anything, it's there. Okay. But if you want to run it on its own, you can just git clone that URL at GitHub and you're off to the races. And it's easy to use. You just have to come to include experimental/MD span, set your include path, and you can use everything. Okay. Those of you who have GPUs, NVIDIA GPUs, or if you just have a CPU and you don't have an NVIDIA GPU, download the NVIDIA compiler from NVIDIA. Okay, download the one installed from a shell script. The smarter one, too smart, says, oh, you don't have an NVIDIA card. So you just download the one that is less smart and you'll be able to install it. I know I did it because I don't have NVIDIA hardware in my own computer. Okay, and you will be able to run, I have a bulleted list there, MD span, sub-MD span, MD array, which is multi-dimensional arrays. It's like array, but that's only single dimension. Linear algebra, and senders and receivers. Senders and receivers is a thing for asynchronous executions that should get into C++ 26, but it's not in it yet. So if we voted in at some point this year, it's in there. Otherwise, it's next standard. NVIDIA has them all in their compiler, runs them now. There's been since 22.7 release. That all of these have been in the NVIDIA compiler, CPU or GPU, they work. And if you want to use them, it's straightforward. You just have to run it with the dash standard option. If you want CPU only, put multi-core. If you're deploying on GPU, then put GPU. What's cool about that is the NVIDIA compiler lets you write ISO compliant code. I'm not joking. ISO C++ code that runs on a CPU. You can use other compilers, run it on CPU. It will let you run that on the GPU. There's certain things that deploys on the GPU. Way, way easier. It does streams and all that automatically for you. Way nice. Very nice. Okay. MD spans. Importantly, some people say, oh, good, these MD spans, they're not costly. They're just playing games with pointers and values internally. So they're fast to copy. There's no memory allocation. There's nothing like that. Okay. And row or column ordering layout. So you have Fortran code or whatever, or you're going back and forth, and that it handles them all. And the C++ 26 standard will even handle more layouts. Okay. There is an accessor policy as well. So if you need to grab a mutex or an atomic for every single access in some sort of shared array, because you're on a shared memory architecture doing things in parallel, you can do that. You can just define your accessor policy and it will implicitly be there. Okay, it's only for dense arrays right now, not shared or not, sorry, sparse. Not really, but you can have varying dimensions. And since the dimensions are quite flexible, people that pioneered this are from the US national labs that do all the supercomputing stuff and figure out the atomic stuff and all this and that. Okay, the nuclear stuff. So this is all solid and thorough. Suppose you have a 5x3x15 array. You want to think of it that way. You can specify 5, 3, and 15 at compile time if it's hard coded. But if you go all the way down to the bottom here, I have everything at runtime, or you might have it mixed up. So the second bullet there, 5 by question mark by 15, you can say 5 dynamic extent 15. The dynamic extent has to be specified at runtime. And if you look at the very bottom bullet, you'll notice on the far right, the variable var is there. I didn't have a good name, so I just put var. You give it a pointer to your data. Remember, it has to be dense. It has to be just big enough to hold the data. And the number 3 is the dynamic extent I chose there. I could have put 50. So if it's some runtime value you don't know, that's what you do. So you have to specify the values that aren't known. Okay, and you can also see there MD span, and you put the whole thing. Yes, it's annoying, but now var is a multi-dimensional view of your data. Okay, so at the top on line 2 here, you can see I have a vector that's 2 times 3 times 4 elements, and I initialize each value to 0. Okay. Then on line 4, I can have a view, a multi-dimensional view of that, 2, 3, 4. Or on line 7, I can have a multi-dimensional view of the 3, 4, 2, or whatever numbers I want, as long as it works with what I have there. Okay, and then I have different things. And then you can see on lines 5 and 8, I can access those elements. And that access is very efficient. Okay, and you can certainly for loop through everything and all that. Hazard pointers. Okay, yep. Just wrap up quickly here. And hazard pointer. What's the deal with hazard pointers? If you're in computer science and you've done data structures, okay, great for sequential programming. Leave the world of sequential programming, most of your data structures off the table, almost all of them. Okay? The reason is in parallel programming, when you have to update something and if you're not using mutexes, okay, it's very hard to you pretty much can only update one word of memory consistently. I'm oversimplifying, but that's good enough. Okay? And your biggest headache is something called the ABA problem. And I'm just going to jump ahead here and just show you hazard pointers. Hazard pointers allow you to clean up and avoid the ABA problem and some other details. So what you'll be able to do in C++ 26 is that line on line 27 there. You'll be able to say make hazard pointer, and then you'll be able to take that value you get back and call the protect method, passing in some pointer. And what you're doing then is you're saying protect this pointer. And as long as that variable, the hazard pointer variable exists, is protected. When it doesn't exist, the destructor will unprotect it. Okay? That's all you have to do outside of one other detail. And to free your memory, okay, that on line 36 there, sorry, my apologies, 37, you call retire on any pointer that you would normally delete at that point, but there could be other threads referring to it, okay, that you call retire and it will get deleted. Memory will be freed, okay. I do have slides here, but hazard pointers are a fast, scalable way for you to do reference counting. Reference counting is not fast. It doesn't scale very well. A lot of cache problems and everything, okay? But if you're in a system without automatic garbage collection, okay, you want to use hazard pointers. Since C++ 11, you've been able to use reference counted pointers, but they're almost all not lock-free. The hazard pointer stuff is lock-free, which translation allows things to race and usually runs a lot faster and solves a whole bunch of other problems. RCU, when do you want to use it? Well, I'll tell you right now, if you use Linux at all, very briefly, RCU is all over the place in Linux. If most of your accesses are reads and a small, and I mean a single digit number or smaller, number of percentage of accesses are updates to that, you can use RCU. Okay? And you can get a lot of performance. Okay? So if you like to use reader-writer mutexes in your code, RCU is a good update replacement. Reader-writer locking doesn't scale well. But when you go up, the core count starts increasing. But RCU does if the number of updates is small. Okay, and I'll jump over this. Linear algebra, BLAS 1, 2, and 3. So those of you who know that, that's basically your symmetric Hermitian triangular matrices, solving them, all that. They're implemented in C++ in the C++ way. They are analogous to the BLAS calls, but there's no ggem call. Those you know BLAS, okay? There's no ggem call, but you'll see there's just a handful of functions and you can call them. And then you'll say one other thing that BLAS you can't do. The D in the ggem refers to double precision. In C++, it's all templated. So if you want to mix your floats and doubles and all that stuff with your vectors and matrices, you can. And the code will be generated. Even better, like this parallel algorithms, all of the C++ linear algebra things allow you to pass in that you want it parallelized. And it will do that in parallel for you. So if you got some crazy matrix multiplication you want to do in parallel, you can. You just add one more argument to the function. Okay. This gives you an idea of how some of those things would be. SIMD, I'll just mention, all of the modern chips will do what's called vector operations. Okay. So you know how they say, oh, you can add 4 integers at a time, or 8 integers at a time, or 16 integers at a time. All these things are very particular to the hardware you're on. The standard SIMD object lets you exploit this explicitly. You can even say, oh, I want this with floats. And it will give you the number of floats that can be treated on that architecture you're compiling for in a SIMD instruction. You can also say, hey, I want so many floats to be in it. You can insist on it, but you can do it the other way around as well. So, and it supports maths and all this, so it's very cool. So I'll leave it at that. And if you want my slides in that, then feel free to share them.
Sure. All right, let's thank Paul for. Any quick questions? Spencer can bring the mic to you.
So, well, like, are you able to use SV slice with MD or standard? Anything?
Am I able to use what with
STD slice?
standard slice?
Yeah.
Okay, the slice stuff comes from the Valeray stuff. The Valeray stuff for everyone here that came into C++ a long time ago. And the only vendor that really exploited Valeray stuff was Intel. What Valeray stuff does is if you have an array of something and you want to multiply everything by 3, you can just take that Valeray, multiply it by 3, and it'll multiply everything by 3. Nobody uses it. It's in C++, so you can use it. If you're using it, great. If you are, I recommend using the Intel compiler because it's the only one that truly takes advantage of all of it and optimizes. But all of these other things were added, and this SIMD thing, quick aside, the SIMD stuff added to the standard, one, the main people working on it was from Intel. So can you use slice with it? I'll just say no. But if you're using Valeray stuff, then you probably can.
Is SIMD like a replacement for Valeray? Or
Sorry?
is SIMD like a replacement for Valeray?
Outside of some small groups, understand almost nobody uses Valeray. There just hasn't been a reason to remove it from the standard. But so everyone on the committee sees that. So we're doing better than that. The linear algebra stuff and the SIMD stuff are improvements on Valeray. Eventually, Valeray probably will go away.
Okay. If there's any further questions, let's we can come up and follow up on stage or any questions. But let's thank Paul again.